And thank you, Michael, and thank you, the committee, for giving me the opportunity to present my research today. I think, Justin, you already did a great job to give a background introduction about my path really to UCF that I joined in 2019. Just maybe a couple of additional words. My research focused mostly on, my background is in computational mechanics, and my research now focused mostly on biomechanics, cardiac mechanics, and electrophysiology, and deployable structure, which are inspired by the maturation of viral capsid. While at UCF, I had the chance to teach different classes several times, dynamics and continuum biomechanics, and then a few other courses. And then we were fortunate to receive recently an NSF award from the Smart and Connected Health program that will allow us to continue the research, part of which I will also present today. So as I said, like my research, mostly one of the main focus of my research is on cardiac mechanics and cardiac kinematics. And the main goal is really to be able to understand the mechanism of cardiac function and dysfunction. And then with this, to be able to develop biomarkers of cardiac health so that we can detect the onset and progression then of cardiac diseases. And the way in which we would like to do this is really using computational models which are microstructurally anchored, that are image-based, and therefore then they can also be tailored to a patient. It can be subject-specific and patient-specific as well. And the way that we want to build this model is really starting from the microstructure. The microstructure is really key to understand cardiac function. In our particular research, we use cardiac MRI to measure the microstructure. And then all the way, once we start adding motion to the microstructure, then we can compute other biomarkers of cardiac function, for example, myofiber strain, which we will talk today. And then all the way we can go to electrophysiology and then later on to mechanics as well. So as I said, like microstructure is really where we start. And if we want like a simplified view of cardiac microstructure, we can think about aggregate cardiomyocyte or preferential direction of the cardiomyocyte, which are the cells that build the heart. And really we're focusing on the left ventricle, that here I'm showing like in a schematic. And then we can think about this aggregate cardiomyocyte to change orientation in a helical fashion, going from the outer wall to the inner wall. And if we look a little bit closer, we can see that these cardiomyocytes are actually organized in sheetlets. And then if we go down, what we really can measure with MR is really aggregate cardiomyocytes. So again, the preferential direction of the cell inside one box. And we can do this by looking at the diffusion of water molecules. Basically, water molecules diffuse more freely along the direction of the cardiomyocyte, and their diffusion is hindering the cross myocyte direction. So we can measure the diffusion of water molecules along several directions, and then we can compose this information, derive a diffusion tensor, and then basically looking at the eigenvectors of this diffusion tensor to be able to then represent this aggregate cardiomyocyte direction at each single slice where we acquire this data. And then, of course, we can compose this data to get a representation of the microstructure for the full. Again, we are looking specifically at the left ventricle, right? So the first things that we would like to do is now, using computational models, try to understand how changes at the microstructural level will be reflected in biomarkers or measures that we can compute from diffusion tensor imaging. So to do that, we have developed, and this is a research which is ongoing, a preliminary model, a very simplified model of cardiac microstructure in which we can simulate the diffusion of water molecules. And then, for example, we can simulate a situation that we will find in a disease. For example, increase in extracellular space. For example, we have the aggregate cardiomyocyte will be farther apart from each other. And this, of course, will change the direction of the direction in which the water molecule can diffuse, and this will be reflected in the data that we measure. And we can simulate how this change at the microstructural level is reflected in CDPI data. So we simulated, for example, mean diffusivity, which of course, as the extracellular space increases, mean diffusivity increases, fractional anisotropy decreases because the material becomes more isotropic, as well as then we can look at these diffusion tensor eigenvalues and the combined measure of these diffusion tensor eigenvalues, which we call here radial diffusivity, which is a biomarker that in a couple of recent publications, we advocate to be a better biomarker that we can derive from diffusion tensor imaging. And then, of course, after the simulation, then we can go back to the images and see how this biomarker that we compute or that changes that we predict in the computational models are reflected in the image that we actually measure. And here is an example. This one are data that is acquired ex vivo, so is a much higher resolution, but we can see and is acquired in a model with an infant, a subject with an infant. They were all like animal data, swine data. We can see here, for example, that the mean diffusivity is increasing the part of where the infant has really happened, and the same, the fractional isotopy has decreased, and the radial diffusivity is again increased. And then we quantify this increase really between the border and the remote myocardium that is in lay terms more healthy, and then again the infant versus remote, and we can see a significant increase in mean diffusivity, for example, and even higher in radial diffusivity that again we think is better biomarker. But then the question is, of course, how this compare to measures that are routinely acquired in the clinic and are already available. And those, for example, can be T1 weighted or LG type of MR sequence. And we can see that, again, the myocardia, the infra region is even brighter, and the increase is even higher than what we can achieve with this new biomarker that we are proposing. So the question is really why then we need diffusion biomarkers if we can do even better with the methods that are available today. And the reasons are two. One is that to acquire T-weighted images or LG images, then we need a contrast agent. And contrast agent is not recommended for all patients. So for some patient population, for example, patient with renal failure, we shouldn't be using contrast agent. And the second reason is that even for other patient population, diffusion biomarkers carry additional information about the microstructural changes. And that's really what is important here, because again, from microstructure then depend cardiac function. And we want to expand this line of research going to in vivo data, which of course is much more challenging because of the noise and because of the lower spatial resolution, and of course to improve the microstructural models that I presented in the previous slide. But then really the jump here is going from microstructure, as I said, is very important because from microstructure, cardiac function depend. And then how does it depend? How we can measure cardiac function once we have an understanding of cardiac microstructure. And that's really the work that we want to do when we measure myofiber strength. Myofiber strength is basically a measure of the shortening, the contraction and relaxation of this aggregate cardiomyocyte that really drives cardiac function. So if we can measure directly their shortening and relaxation, then we have direct measure of cardiac function. So that is an ideal biomarker to, again, characterize the onset and progression of the disease. And the second advantage is that this measure don't depend on an arbitrary reference system. What is usually done today is that we use this longitudinal, radial, and circumferential reference system, but this depends on the observer. And introduce an arbitrariness in the measure, in the cardiac strain that we actually measure. Myofiber strain actually sidestep this problem, right? So then how we can do it, and the first way that we did it is basically combining dense and CDTI, or two types of MR sequence. Basically, dense MRI allows to compute motion, point-wise displacement actually, and CDTI allows to compute cardiac microstructure, as I just mentioned in the previous slides. And then we can interpolate the displacement, differentiate the displacement projected along the direction of the cardiomyocyte and compute myofiber strain, and that's actually what we did in several cases, both in human and in animal studies. Okay? So this seems ideal, but unfortunately there are two problems with this method, right? So this is great because we can compute myofiber strain, but still to bring this to the clinic, we still have at least two problems to face. The first one is that this method is based on differentiated displacement field. And since displacement field that we acquire with the images is noisy, then as soon as we differentiate the displacement field, then we increase the noise in the data. And then, of course, that will be reflected in noisy myofiber strength measures. And the second problem is that these sequences are quite expensive in terms of times and in terms of the skills that are needed to be able to acquire this type of data. It's not what is routinely done in the field. So then how can we do it without using this type of sequence and without having to differentiate the displacement field? And that's really what we want to do next, is computing myofiber strain based only on surface motion. So seeing MRI is routinely acquired in the clinic and give us the motion of the inner and outer surface of the heart. And then we can build a model based on the seen MRI information and the microstructure information, and that we can combine a finite element model, which is not a mechanics model. We want to develop a kinematics model. I can get more into the details if there is interest there. But basically then we have a model and we have surface data. By comparing the two, and matching the two as best as possible, we can compute what myofiber strain will be on a patient-specific basis. Then you can imagine that doing this, we're required to do a lot of segmentation, a lot of model building. Again, if you want to do it in a clinical setting, we cannot do this manually. But this is a task which is perfect for machine learning, and that's really a second aspect that we want to develop, and is basically using short axis and long axis images that we can acquire, for example, from MR, all the way to compute models of the left ventricle. And this, so there is a lot of work has been done on segmentation. Really what we want to do here is model building more than segmentation, and then combining longitudinal and short axis information. But that's not the only innovation that we have here. Another part that we're very interested in is actually in quantifying the uncertainty that is containing this model, right? And doing this, our machine learning framework allows us to have a sharper measure of the uncertainty in the model. And this, how we propagate then this uncertainty in the model all the way to the measure of myofiber strain and other cardiac strain that we can compute. And this is really key then to, again, be able to use this data in the clinic. So really the goal here in the future is to be able to enable real-time strain calculation from data, which is routinely acquired, and then to provide, together with the measure of strain, also a measure of the uncertainty and the confidence interval that comes with this strain. So that's really the direction that we are taking this project with the grant that NSF just funded. And then let me conclude just by thanking all the people that work with me on this project, current and past students and collaborators that made all this research possible. And again, NSF for funding this research in the next few years. Thank you all for your attention. I'll be happy to take any questions, comments, and suggestions. Thank you.